Okay, so what we're doing is sketching the graph of the basic reciprocal function, horizontally shifting at some distance and vertically shifting at some distance. Horizontal shift will be positive, vertical shift will be negative. So we start, I mean, the instruction says, most people, the instruction says, sketch a graph of the basic reciprocal function. Okay. Well, you kind of want to start with that. But if you start by doing it from the usual domain and range, you're not going to have room on your graph to move it. So ideally, you say, okay, I'm going to have to shift this far and this far, so I'm going to have to give myself room for those shifts. If not, well, you have the graph and then you have to make another graph. That's not a big deal. That's what most of you did. And then we want to give the equation of the transform function. Now, again, we're anticipating this a little bit early. The actual assignment of this won't be due until next week, section in your text, but this is one that people stumble over like crazy. So we want to anticipate it early, get your mind working on it so that by the time the assignment is actually due, you're ready to do it. People did quite well with the transforming points assignment. Okay. I got a bunch of those. Some people had the question. My graph doesn't have room to do that, so you kind of have to change your scale a little bit. And that's kind of my fault. I assigned your ABC numbers and did check to see if that was going to work with all the instructions on the assignment. It always works, but I use bigger ABC numbers this time. My fault. Okay, most people did the adjustment, but if you didn't, just go ahead and do it and get it in. Okay, but people did quite well with it. Okay, so anyhow, here we go. Since I'm going to be shifting to the right, I'm not really going to need X numbers, much less than -2, because everything's going to shift right. And the lowest X number I have here, the least X number is -2. So I'm going to set the scale up to give myself more room to the right. And since I'm shifting 5 units, well, I know then that the biggest X value I'm going to get is going to be 7. I'm going to shift 2 over 7. So what I'm going to do is I'm going to start by, I'm going to use 8 because it's easy to subdivide. Halfway between 0 and 8 is 4. Halfway between 0 and 4 is 2. Halfway between 0 and 2 is 1. And then we have 1/2 from 4. It's the easiest way to set it up. Then I can fill in numbers over here, and I will as I need them. And then if 2 is here, then well, -2 should be about here. You can push it to the other side. And the y-axis. So I have 1, and then I have -1. -1/2, -1. Now I can plot my points, except I have to get my vertical scale. Now my vertical scale has to go up to at least 4 here. And it has to go down as far as -7, doesn't it? So all my numbers, none of my numbers here are negative. Okay, so if I lower all these 7 units, none of my numbers are going to quite be as low as -7, but some of them are going to be just -7 plus 1/4, -6 3/4. So I'm going to be safe if I use -8. Then I have -4 here. I'm not going to label these points because they are. But there's -2, -1, then -1/2, -1/4. If I need it. Up here, then if that's -4, this will be +4. So here's 4. And then I'll have my 2 and my 1 and my 1/2. And now I can plot my points. So -2, 1, 4. X is -2. Well, X is -2 here. y equals 1/4 along this line. Well, I'm not going to label that, but there's my y equals 1/4 line. And there's my point. And then negative. See what I did? In this hurry. I got rid of everything, put those out of order. No, I'm wrong. Thought I made a mistake, but I didn't. Okay, now, negative 1, 1. Okay, so we have negative 1, 1. And then we have negative 1/2, 4. So here's negative 1/2, here's 4. Well, that gives us the familiar graph. I'm going to draw the other side of the graph. That's not okay. And if I want to make the curve, and most people like to make the curve, remember the curve represents what I'm calling the extended basic function. The basic function consists just of these 6 points. Okay. And we think point by point. We're just going to move these points, each point, the way we say. We're going to move each point 5 units to the right. I'm not going to label the coordinates to every point, but I'll label this one. And I'll label this one. And I'll look at what happens to this point and this point, and that should be obvious what happens to this point. So I move each of these points 5 units to the right. Well, okay, this point, x equals 2, it's going to move over to where x equals 7. Well, where's x equals 7? 4 is here and 8 is here, 6 is halfway between, and then 7's here, and 5 is here. So I can safely, say there's 5, 6, 7. Okay, so the x equals 2 point moves over to x equals 7. The y value doesn't change yet. So I'm going to move this point over. Put a little 5 there, meaning this is an arrow of length 5. And I can use that arrow. I can just pick up that arrow, move it up here and down here to depict what's going to happen. Okay, well, if I take this point, I'll move over 5 units. Okay, some point over here. It's actually going to be, so you can figure out what the coordinates are going to be. So if I move 1/4, 4, 5 units over here, well, this becomes 5 1/4, 4, because I'm changing the x coordinate. I'm adding 5 to the x coordinate. I add 5 to the x coordinate here, and I get 0.714. And then here I'm going to get to 0.61. I can label this point, it's just going to get nasty. Okay. So there are 3 points. Now, moving these 3 points over, well, -2 move over 5 units, go over to or x equals 3. So I'm going to get a point here, and I'm not going to indicate transformation. I move 5 units from here to here. It gives me the point 3 1/4, right? So I can label that point. There's 3 1/4 here. And then -1 1 is going to go to 4 1. And -1/2 4. Made another mistake. I don't know what y'all are doing. ruined my brain today, but it must be your fault. Okay. Okay. It's not 1/4 4, it's 1/2 4. And this would be 5 1/2 4, not 5 1/4 4. Okay, so I move the point 1/2 4 over 5 units, and it gives me the point 4 1/2. So I've got a point right here, which is 4 1/2 4, but I'm not going to label. And so I can draw a curve here and a curve here. And we see the entire graph is moved over this point. In addition, the y-axis is moved over 5 units. I move the y-axis over 5 units, then I get the line y equals 5. X equals 5, sorry. There's the y-axis shifted 5 units to the right. Okay, well now I lower all these points 7 units. Yeah, that's pretty straightforward. First of all, let's find -7. That's going to be important. This is the x-axis shifted 7 units. Okay, so now it's going to be pretty easy to locate this point. This y coordinate isn't going to change. Y starts x coordinate is not going to change. It's still going to be 7. It's going to be in this vertical line through x equals 7. And it's going to still be, well, it's a 1/4 of a unit above the x-axis. We move it down, it's going to be a 1/4 of a unit above the line x equals -7. So it's going to be here. And we can see that that point is going to be and -6 3/4, which is 1/4 of a unit above -7. Make sense? Okay. So 5 1/2 4, go down 7 units. So I can write 5 1/2 there here. 5 1/2 4. Go down 7 units, and you're down to -3/2, -1 1/2. So this point, I'm sorry, 5 1/2 4, you move down 7 units, you're going to be down at -3. So there's -4, there's -2, so -3 would give you. So at this point, I'm going to transform down to about here. That's 5 1/2 -3. Then we're going to get 6 1 is going to go down to 6 -6. And I'm going to get something that looks like this. Then your other points, I'm not going to go through the detail on those. Going to look the same on the other side of the line x equals 5. And the big thing I want to be sure we see is that the vertical asymptote, which was at the y-axis, is now at x equals 5. Okay, so this is the new vertical asymptote. And x equals -7 is the new horizontal asymptote. It's because this thing, the original function is going to just continue approaching the x-axis, but never reaching it, and have a horizontal asymptote. So this is the new horizontal asymptote. Now, by the rule that I think we talked about, and if we didn't, we're going to prove it here, because I think we did this. The formula for the transform function. Well, I'm going to do the formula for this one, then I'll do the formula for this. Okay. The original function y equals 1 over x squared. The horizontally shifted function is y equals 1 over the quantity x minus 5 squared, not x plus 5 squared. And we're going to test that and make sure that it really works. Then the horizontally and vertically shifted function is is 1 over the quantity x minus 5 squared minus 7. We're going to verify that. So I'm going to ask you to do calculation. If x equals 6, let's say 7. X equals 7, what values do you get for the horizontally shifted function and for the vertically shifted function? And to answer that question, you're just going to plug x equals 7 into the horizontally shifted function and see what you get. And then you're going to plug x equals 7 into the vertically shifted function and see what you get. Okay, so a horizontally shifted function get y equals 1 over 7 minus 5 squared, which is 1/4. Okay. Oh, does that match anything on the graph? Well, this says when x equals 7, y is 1/4, right? That would imply the point 7 1/4. X equals 7, y is 1/4. And right there it is. Okay. If you plug any of these other x coordinates in, to this function, you're going to get the y values on the graph. So this connects the arithmetic with the graph. And the idea that the horizontal shift has to be x minus 5. If it was x plus 5, and you plug in x equals 7, you get 1 over 144. Doesn't match anything on the graph, right? Okay. It turned out if it was x plus 5 squared, that graph would be 5 units over this one, the original, because that would shift it to the left. And you could prove that easily just by doing everything we did here, but shift it to the left. And then test that against 1 over x plus 5 squared. Okay, well, if we do, I'll just write both shifts. I'm going to write down here along the board. We get y equals 1 over 7 minus 5 squared minus 7, which is 1/4 minus 7. You do the common denominator, you're going to get negative 27 over 4. But also, you can just kind of do it in a number line. If you go down 7 and then up 1/4, you're at 6 3/4. Either way, you get 27/4 if you do your fraction calculations methodically. And it's a good idea to do that. So make sure you're doing it right. Or just by inspection, you go down 7, up 1/4, you know you're at negative 6 3/4. Okay. And of course, that matches the coordinates here. Showing that this whole rule, if you shift horizontally, you replace x by x minus whatever the shift is. If you shift vertically, you replace y by y plus whatever the shift is. In this case, the shift is negative 7. So y, this plus negative 7 is just this minus 7, right? Now, if you understand that, and understand in terms of all the basic functions, then you're going to be in pretty good shape. And this is, in my opinion, extremely important because in many places, calculus courses and then courses beyond calculus, although most of you aren't going to go much beyond calculus. Okay, in the curriculum you're in, you probably won't have room in your schedule unless you decide to become an engineer or mathematician or physicist. Okay, of course, most of you want to do that, right? No, you have other interests. Okay, yeah, so mathematics really all of a sudden stimulates your brain, and you want to follow that path. Follow it as far as you can, see if you do. But the point is that even in an applied calculus course, the rules in applied calculus you can understand much more easily if you understand transformations. Everything becomes simple and straightforward, no matter how complicated it looks in your textbook, because they don't assume that you understand transformations. Okay. They know that most people are going to come out of pre-calculus not understanding it, so they can't do it the easy way. So it's one of the ways we build new functions out of our toolkit functions. Oh, bad words. That was also good. That would have been, talk about viral. That would have been super viral. Oh, I hate it. Just to recapitulate what I said so beautifully. And my words are now echoing throughout the universe that nobody's going to pick them up. So I'm going to have to do this just in a quick. What I've said is your general rule for shifting a function horizontally or vertically, Shifting it horizontally, you replace x by x minus whatever your shift is. Function notation gives us a beautiful and concise way of saying this. It says if we got y equals f of x, in this case, it would be f of x equals 1 over x squared. You get a new function. If you take that function, move every point h units horizontally, you have the graph of the function g of x equals f of x minus h. Where you replaced x by x minus h, just as we did here. X replaced by x minus 5 in this case. Y equals f of x, moved k units vertically, gives us a new function, s of x equals f of x plus k. And that plus looks so much like multiplications. Since this is going to still go viral, but not as well as the other one. This f of x plus k is there. Can't go viral if you're not. Okay. It says we move it k units vertically, then our new function, which we can call s of x, we can use any letter we want. This new function is now f of x plus k. So we did that here. But we didn't actually do it. We didn't do f of x plus k. What we did was we combined both shifts to get a new function I call u of x. U of x is f of x minus h plus k. What's f of x minus h? Well, that's your 1 over x minus 5 squared. What do you get when you add k? K is your vertical shift, which is -7. So that's going to give you 1 over x minus 5 squared minus 7, which is exactly what function notation would do if f of x is your reciprocal square function, h is 5, and k is -7. So I've labeled the functions, and I've actually thrown in the g of x is going to be 1 over x minus 5 squared. Correspond to this substitution, this compound. And then if you do both shifts, which we did here, and we call it u of x, f of x minus h, which was your 1 over x minus 5 squared, and then plus k, k being -7. There's your -7. There's your u of x function. Here it is. Here's our u of x function. Here's our g of x function. If you totally understand that, you've got something pretty good. Because as I said, so wonderfully, it'll never be said this well again. And I'm not going to be able to say it as well because I've said what I said before. But the beauty of function notation is it allows us to write a rule or a set of formulas for doing this stuff, and it applies to any function whatsoever. Okay. And again, the reason I stress this so much is this is how one of the ways we build new functions out of old functions. Okay. One of the ways we build our functions, almost all the functions you're going to ever need out of our basic toolkit functions. One way is by doing shifts and stretches, which we'll talk about a little more later. And then by doing composites. Okay. So you can build just about any function you need if you have a mastery of those things. And that's what's really important about this course, not so much the algebra, but of course you need the algebra to execute. And the focus of this course is on functions. It's on the way they behave. It's on the way the graphs look. It's on the way it's on what they tell you about what's going on in the world. Okay. And that's where they're really, so that's worth taking time. So you have to listen to it again, but there it is. You maybe understand it better the second time, so maybe it was worth the time. Okay, we've seen a lot about transformations. I want to shift gears to the topic you're going to have for homework. Don't think it's overly difficult assignment. If I find out differently, we should spend time on it. And we'll spend some time on it. You're going to have a quiz on it next time. It's the idea of rate of change. Now, I just got done saying that transformations and composite functions are how you build functions. Rate of change is one of the two most important properties of functions. Okay, so you're seeing big stuff right now. And again, we just have to try to work through the details of it through the rest of the course. First chapter, you're seeing the big important stuff. We use ROC, so I don't have to keep writing the word and saves us time. Now, just say yes or no. We talked about rate of change a little bit in here. Okay. Didn't think so. I generally make notes about what we talk about. I like to check it against the reality because it sometimes makes mistakes. Okay. Rate of change of a function is defined here. The average rate of change of y with respect to x change in y divided by the change in x. Now, a lot of times in your open math is probably going to define it by a formula. Okay. Formula is okay, but I like to start with the idea. Okay. So let's just talk about a change in y and a change in x. Let's say, I'm not going to write this down, so you kind of jot down the numbers. Let's say that I make what? How much money do you want to make? Say I make $5 million in 10 days. Okay, you can make that. Okay, I don't have to be responsible for that much money. Okay, actually, depending what I had to do for it, there are limits. So if I make $5 million in 10 days, at what rate would you say that I'm making money? We're going to stop and talk about this for a minute. Okay, so we established, for example, if you make $5 million in 10 days, then to find the rate at which the average rate, because you might be making more in one day than the other, okay? But you can average the rate by simply figuring out how much per day. That would be a rate. Okay, how much per day? Well, you're going to divide the $5 million by the 10 days. Gives you $500,000. And you ought to be able to visualize numbers like that because with inflation, lifetime earnings, most of us are looking at in the billions of dollars, okay? Even at minimum wage, if you work for 90 years. Okay. So you want to be able to think up to into the millions without having to just punch it into a calculator. Obviously, to get the accurate numbers, you should calculate. So you want to be able to visualize at least $10 million range. Okay. So what we divided was the change in your wealth, which would be $10 million, divided by the change in time, which is 10 days. So example, $5 million. So we write that as $500,000 per day. Okay, 300 miles. That's the change in our position. Divide that by 6 hours or 5 hours, let's say. Okay. Well, if I have a graph that starts out as a graph of basic exponential, but I change the scale so that here is 30 years, and here is, let's say, $60,000. Okay. Now, according to this graph, how much money do you have after 10 years? Just look at the graph, all one if you like, and visualize, and maybe write down how much money you think you have after 10 years. Okay, now I didn't give you a lot of time to process this question, but to answer the question, how much money you have after 10 years from the graph, you find 10 years on the graph. Where's that going to be? Up here? No, it's going to be obviously going to be about here. So maybe this is 10 years. Maybe this is 20 years, right? And then here's how much money you have after 10 years. Okay. And it looks like, let's see, 1, 2, 3, almost 4. I'm exaggerating a little bit. $15,000 wouldn't be that much. Okay. I'm thinking it's probably around 17 or 18,000, but I'm going to use rounder numbers. 15. $1,000 for 10 years. Okay, then how much do you have after 20 years? Make an estimate, jot something down. Even if it's a lot of you photo of the graph and stuff, so I'm going to go on here. And what we do in the graph is this. Okay, well, what's that? Well, $60,000 halfway down here would be 30,000. That's a little less than 30,000. So maybe $25,000. Okay. Now, what's the change in what? Yes, this is time, I'm going to use t instead of x. So it's y and t, but it's going to be change in y divided by change in t, right? What's a change in y? What's a change in t? According to my numbers, what was the change in y? Show me with your fingers how many tens of thousands of dollars, or how many, yeah. Okay, $10,000, right? Okay, change in y is, well, it's going to be that's the word there is dollars. And t, change in t is what? Well, t changes from 10 to 20. That's 20 minus 10. Years, that's 10 years, right? So what's the average rate? What I define average rate to be, what did we do? We divide something, but divide one thing by the other, right? The change in one thing divided by the change in the other. Yeah, so it's going to be $10,000 over 10 years, $10,000 per year. If you have a formula for this function, of course, you don't have to make estimates. You can plug numbers into the formula. If I ask you for the average rate of change of the x squared function between x equals 1.5 and x equals 2.5, you plug 1.5 into the function, you plug 2.5 in, you get the two y values, subtract them, and you divide that by the change in the x value. Okay. Spent a little more time on transformations than I intended to, but I think that should give you the idea of the rate of change. The arithmetic, the algebra of it is fairly simple in most cases. Open Math does a good job of explaining it to you, but they explain it to you, I think, more in terms of a formula than in terms of an idea. So I'm trying to give you the idea. Make sure you think about the idea as well as apply the formula just to get the right answer, okay?